Today's webinar will be provided by Mr. John Clark from CSIRO on the climate thresholds tool within the Climate Change in Australia Climate Projections website. So we might jump straight in. John leads the outreach component of the Earth Systems and Climate Change Hub Project 2.6, which is the regional projection science and information and services project. So he's close to a decade's experience developing and delivering climate projections tailored to the needs of practitioners and researchers in the climate impacts and adaptation field. So John and the regional projections team previously led the development of the Climate Change in Australia website and its 14 web tools, including the thresholds calculator, which John will be talking about today. So I might hand over to John, who's going to give a bit of a background to the tool and some demonstrations. A little bit of housekeeping to begin with. If you have any questions, please, there's a little chat box at the bottom of Zoom. Please do pop your questions throughout the presentations in the chat box. And at the end of the presentation, we'll have a facilitated question and answer session where I'll be reading out the questions for John to answer. If you have any issues with the audio of John or his visuals, please do also write in that chat box, as I'll be monitoring that and try to fix anything that goes astray. So without further ado, I'll pass over to John. Thanks, John.
Thanks, Sonia, and welcome. What we're going to look at today is a new version of the climate thresholds. So as Sonia mentioned, it's one of 14 tools available on the website, and this tool's been available since the website was first launched, but we've just upgraded the tool and added a bunch of new features. So that's what I'll be running through today. So we'll do it in the form of a live demonstration, so there won't be any PowerPoint slides today. So in a nutshell, exploring thresholds is a useful way to get a bit of a feel for projected future climatic extremes. So you can think about things like, you know, how many days per year is it expected to be above or below a particular temperature threshold, or a particular rainfall statistic, or the number of months per year, you know, that might be below a particular rainfall threshold, things like that. So that's the approach that this tool uses, and it's really quite straightforward, but there's some important things to understand about the underlying data and what it's good to be used for and some of the limitations around it as well. So I'll start with just giving you a quick look at the website, and then we'll run into how to use the tool, and then I'll talk a bit about the methods that we use to develop the data that are presented in the tool, and then just some tips on using those data sets. All right, so hopefully you can see the website landing page now. Just note the URL, if you don't already know it, it's pretty easy to remember, www.climatechangeinaustralia.gov.au, and that will get you to the website. Just really quickly, the website is divided into 4 parts, and they're represented by the 4 large swatches on the homepage, and we're going to focus in on the projections and data section today because that's where all of the tools are. But it's worth knowing that particularly the Climate Campus and the Getting Started tabs provide you with a host of information about either how to use the website and the tools in the Getting Started section, or the fundamentals of climate science and associated matters in the Climate Campus. There is a wealth of information in those sections. And a couple of other things to point out to you is there's a news and updates page if you're not aware of it, and if you click on that, it just takes you to a list of announcements, including things like downtime. So if you're having trouble with the website, always good to check here to see if it's a known outage, but also announcements like the launch of the Thresholds Calculator version 2, for example. Okay, if we just jump back, I'll take you now into the Thresholds Calculator tool. So it's in the Projections and Data section. Click on that. And in this second level menu that's appeared now, you can access all of the tools and a bunch of associated bits and pieces. The Thresholds Calculator is down here underneath Explore Data. Now, as soon as the page loads, the new feature that we've just launched is that depending on your location settings, you will be presented with some default results. I've got my location settings set to prompt me each time as to whether I want to allow it or not. So I'll allow the website to know my location, and it reckons I'm in Cranbourne, which isn't far off the mark, and presents me straight away with a table of results. Now, if you've looked at the thresholds calculator before, you'll notice that this is quite different. Previously, you were not shown any results when the page first loaded, and you could only obtain results for one model at a time. So that was a bit of a limitation. So what we've done is we now present the results from all 8 models. So what it's showing here is the maximum temperature, average number of days per year above 30 degrees Celsius for 2030 under RCP 8.5, as it shows here. So that column down here on the right shows the average number of days per year as projected by each of the 8 models. And the model at the top at the moment, Access 1.0, has an asterisk next to it. That's just to denote that that is the model that's currently displayed on the map in the background. Underneath the individual model results, we present summary statistics. So these are derived just from these, the results from these 8 models. So it's just a simple minimum and maximum and mean calculated from those 8 models. So it's important to appreciate that you'll get a different result for these thresholds depending which model you look at. So by presenting the min, max and mean all together as a summary on this pop-up, it's a useful way to get a feel for how much of a range there is between the minimum and maximum projected value and just where the sort of midpoint sits. Now, if I pack that away, click on the X and hide it, you can see now that the map is showing the results that I just described. Access 1.0 for 2030 under high emissions for maximum temperature and 30 degrees Celsius. So just quickly, to use the map, if you haven't used it before, you can use these plus and minus buttons to zoom in and zoom out, or you can double click anywhere on the map to zoom in, and you can go in reasonably close, but that's the limit. Once you zoom in all the way, you can see now that the results are actually little pixels. These are 5 kilometre grids, and I'll explain that in a minute. You can also see the legend on the right, which shows you the colour scheme that's used to present the results. And if you want, you can change the overlay that's used in the display. By default, it's showing the natural resource management regions that were used for these set of projections. You can change that to display states. All it's doing though is just putting an overlay over the top of the map. It doesn't, there's nothing interactive there. Now, if I want to change these settings, I go down to the configure data section, and if I click on where it says variable, I can choose from 3 now. Previously with version 1, we only had minimum and maximum temperature, but now we have rainfall as well. If I go to minimum temperature, we've just had a look at some maximum temperature results. So if I have a look at minimum temperature, then if I choose the threshold of interest, you can see that there's 2 sections. It's a bit hard to read, but this one says days greater than, and below that, days less than. Now, this is similar to the way it used to be with version 1, but there are many more thresholds have been computed, and they're all now available through the tool. For example, you can now look at days where the minimum temperature was less than 22, which is quite high, but it's quite relevant to some sectors. So if we say we want to see days where the minimum temperature is greater than 24 degrees, which is a threshold of interest to some agricultural activities, And we can look at that same model again, or we can choose a different model if we want to. I'm going to choose a different emissions scenario, and I'm going to look later in the century, maybe 2070. And once I'm happy with those settings, I'll leave season at annual for now, but I could choose any of these 4 seasons there, or the wet dry season used in the tropics, or individual months, but I'll stick with annual for the time being. So to show those results, I have to redraw the map. So I'll click on that, I wait for it to draw, and it's now showing me the results for this model, GFDL. Now, if I want to, I can click on a location, just interactively on the map. It takes a little while, going off and doing a bit of thinking, and then presents the results. I'll just close that again and show you the alternative way to bring up location results, and that's to use this select locality drop-down list. And if I type the letter B, jumps to the Bs, and there's Bendigo. And again, the results pop up. So again, it's summarizing, it's explaining what these results represent. What I didn't point out before is this important line here, which is the number of days computed from the historic period. So they're useful for comparison, obviously, with the future periods that are presented below. Something to mention with this too is in version 1, we provided a download link for the tabulated data. Because it's now presenting this more sophisticated set of results, that's much more difficult to do. So if you want to grab these results, you can quite simply select them with your mouse and copy. And if you paste that into Excel, it works really nicely. So that's, at the moment, the best way to get hold of those numbers. Hopefully in future, we'll be able to enable that download again, but it's not currently available. Speaking of download, if I hide that box and go back to the map, if you've been using version 1 of this tool, you will have remembered that you could download the gridded data that underlie this map. And once again, that's not currently available in this new version. It's something that we're working on and hope to be able to enable again in future. But if you do want to obtain those data, you can request them from us. All you have to do is go up to the mega menu at the top, go across to the Contact Us page, and there's a data request form there. Fill that out and email it in, and we'll get back to you. So you can obtain the gridded thresholds data. So remember, this is on the 5 kilometre grid. So if I zoom back in again, you can see the pixels here. These are 5 kilometres up and down and across. So you can obtain those data for each of the 8 models, and we also have a version of these data that provide the summary data, summary statistics, so minimum, maximum, and mean, and that's for the entire data set across the whole country. So you're not restricted to just those 400 plus locations that are available in the locality selector, but the tool doesn't allow you to access those interactively. You can access these 400 sites interactively, but you can't just click on the map and pull up data for any location. It's something we're considering for version 3 of the tool, but we haven't implemented that yet. The reason being that we made a decision early on that we would present a consistent set of locations among the different tools, and some of the other tools use locations, and so they all use the same set. But we're reconsidering that at the moment. If you would like to let us know your thoughts on that, we'd appreciate it. All right. So we've looked at maximum temperature, minimum temperature. Now I'm going to show you the rainfall settings, because it's really quite different from the temperature and the minimum and maximum temperature data. There are two different metrics available that relate to rainfall. The first is the number of days per year where the rainfall exceeds the 99.9th percentile. So rather than a fixed threshold like we use for temperature, such as 30 degrees, in this instance, it's more meaningful to look at the results relative to the historic results. So by looking at the 99.9 percentile, it's looking for the number of days that exceed that historic statistic. So if I select number of days greater than the 99.9th, and I'll just leave those settings as they were, redraw the map, you can see it looks quite different. There's a couple of things to explain here, and I'll say a little bit more about this shortly, but it gets very messy in parts of the arid zone, and I'll explain why that is, but essentially there are no data in some of these regions. It's just a fact of life with that particular historic data set. But you can see that it's a much more complicated pattern than we were seeing for the temperature-related statistics. So if we choose a location, click on Dubbo, you can see it presents the results in the same way. The historic value at the top, so that's saying that there are, on average, 0.41 days a year where the daily rainfall has exceeded that percentile. And that 99.9th percentile, that's 1 in 1,000 days. 1 day in every 1,000 days on average, you would expect a rainfall event to exceed that threshold, and that's approximately once every 3 years, slightly less than 3 years. And importantly, note that it's calculated over this 30-year period, 1981 to 2010. And then, as before, it's giving us the results from each of the 8 models, and you can see there's a range, and that range is summarized down here: minimum, maximum, and mean. And notice that the asterisk is no longer next to Access 10, it's now sitting next to GFDL ESM2M. That's because I selected that model earlier on, and that's the one that's displayed on the map. Just check my notes, make sure I'm not forgetting anything. Okay. Now the other rainfall metric that we've added in is this one here, the number of months less than percentile, and the percentile is the 10th percentile. So the 10th percentile is basically the point at which 90% of all of the records exceed that amount of rainfall in a month. So it's a metric of dry months, if you like. And because we're counting the number of dry months per year, it's an indicator of dry years, effectively. So again, if I leave, I might just change the model. Let's grab that one. Redraw the map. And now we're seeing representation of the average number of months per year that have a total rainfall below that 10th percentile, so dry months. If I choose a location, let's have a look at Ballarat. You can see here that historically, in that 1981 to 2010 period, there were 1.24 months per year on average. And this is the range that's projected into the future, with a maximum of 2.86. So more than double the maximum. The minimum is a small increase over the historic. And the mean number is 1.6 months per year. And that's computed over a calendar year. If you're familiar with the Coast Adapt website that the National Climate Change Adaptation Research Facility developed, they use these data as well. We provided these data to them for their website as well. But they use a different definition of the year. So we're using the calendar year here. On their website, they wanted to specifically look at an offset year from May to April. So there's a difference in those data if you ever have cause to compare the results. Okay. One other thing to mention, I said before that we can choose any of these 8 models to display on the map, but we can also display the historical data. If I redraw the map now, it's now showing the historic data for that same metric. Incidentally, if you want a copy of this map, you can't download it, but you can screenshot it. So if you're familiar with screenshotting, or if you have some screen capture software, you can grab it that way. I use Firefox, and Firefox has this really neat take a screenshot feature, which means I can just click it and download it, and it's all hunky-dory. All right. If you're, just getting back to these configuration settings, if you're unsure about what any of these things mean, say emission scenarios, for example, there are a range of information explaining what these things are on the website, and you can see here from this breadcrumb trail here that we're in the climate campus under modelling and projections, projecting future climate, an explanation of greenhouse gas scenarios, including the 4 RCPs, which are the current ones. And also in this supporting information, you can find an explanation as to why we're only providing you with the results from 8 models. So just go back to the thresholds calculator for a second. I've sort of just, you know, in passing said you can choose from any of these 8 models. Well, why those 8? Those 8 models have been chosen because they are representative of the range in projected changes across the whole country in terms of their monthly, seasonal and annual changes in temperature, rainfall and wind. In addition to that, they've also been chosen because they are all models that perform well in reproducing the historic climate, so that gives us confidence in their results. And the third thing we take into account is model independence. Because global climate models are very complicated beasts, different research groups around the world share their code and share modules of their models. This gives them a degree of interrelatedness. But in terms of exploring the projected changes in terms of individual models that represent the range of change, ideally we would have completely independent models. So what we've done is we've looked at an analysis that was done internationally, and these models are as unrelated as any, if you like. They all are somewhat related, but these are less interrelated than many of them. So they're the 3 main parameters we took into account in selecting those 8 models. And the ultimate goal was to make it possible for people to explore the projected changes without having to consider results from 40 models. So basically cutting it down to 8. That was the smallest number we could get to without losing important information. The other thing to explain is with the time periods, notice that there's a range of years in brackets after the first number. What it's telling us is that essentially, if I choose 2050, we're looking at the projected changes as they relate to the mean climate around 2050. But in terms of the actual years that are used in the calculations, they span from 2036 to 2065. So it's a 30-year data set, and that matches up with the historic data that we used, and it also aligns with the projected change values that we used in computing the data, which I'll explain shortly. Okay. With all of the tools that we've developed on the website, there's a bunch of information underneath the main part of the tool. And usually it starts with essentially a how to use this tool section, and then further down the methods and limitations. So I just want to speak a little bit about the methods that underpin this tool. So I've mentioned the 8 model data set. What we've done is we've computed a future time series at daily time steps by combining the historic data in the form of a daily time series for 30 years from a data set that was produced for the Australian Water Availability Project. These data are on a 5-kilometre grid across the whole country. It kind of peters out a bit near the coast sometimes, which causes us a bit of grief. But essentially, this is a robust data set that provides us with historic information for the whole country. Because if you're familiar with, if you've looked a lot at the Bureau of Meteorology's website and looked at getting climate data from them, you'll be aware that the distribution of Bureau stations across the country is pretty uneven. You know, there's a real clustering of stations in the southeast, and there's very few through the middle, the rangelands part of Australia. So in order for us to be able to develop analyses of future climate across the whole country, we need a way of accessing historic data for those blank spaces, if you like. So a common approach, and this is used internationally as well as in Australia, a common approach is to use a modelling approach to infill data between the stations. And so you use a model to do that, and it's a climate model, so the results are meaningful. It's not just a simple interpolation. It takes account of elevation and the region and so forth. But basically, they infill the data between the stations, and there are a bunch of methods that you can use to do this. And depending which method you use, you'll get a different set of results. So for Australia, we have 2 well-known gridded data sets at this resolution for all of Australia. One is this AWAP data set that we've used. The other is the silo data set that was produced by Queensland, and it covers the whole country. And they use different methods. So you get different results depending which historic data set you use. And they each have their strengths and weaknesses. The AWAP data are optimized for getting the results correct across areas, whereas the silo data are optimized, as I understand it at least, to get the results right at point locations, and because they have a different emphasis there, which is much more about farm scale information. So something to keep in mind. But to produce the future versions of these data, we take the 30-year time series and we apply the projected changes from these 8 climate models onto those historic data. So for example, the maximum temperature recorded on the 1st of January at the beginning of the 30-year time period will be modified by the projected change for January in the future time period that we're interested in. So if we're looking at 2050, then we would apply the projected change in maximum temperature for January in the climate of 2050, and so forth through the 30 years of daily records until we end up with a 30-year time series that is representative of the future. It's plausible, but it's not a prediction. So even though we say these data go from 2036 to 2065, we're not saying this is how the weather's going to look in 2036. That's not what we're doing. What we're trying to do is characterize a plausible sequence at daily time steps that is consistent with the mean climate of that future time under this emission scenario. So they're the underlying data. And then once you have that daily time series, you can then quite simply just go through and count how many days in that 30 years are above a threshold of interest. And then you get that total, you divide it by 30, and there's your average per year, which are the results that we're displaying through this tool. So a few things to know and keep in mind when you want to use these data. And the first is that, as I just explained, the infilling of data in the historic data set means that there are going to be inaccuracies. That is just inherent. And because of the method that's used, it also means that if you zoom in to a place where you know there's a weather station, say Melbourne, if we pull out the results from Melbourne and compare them to data from the Melbourne Bureau station, they won't match. And that's because in order to infill the results, infill the data between the stations, this approach allows the station data to be changed, or the data that correspond to the location of the station, in order to get the most, to get the fewest errors, if you like, throughout the entire data set. So that means if you're looking at an area where there are a high density of Bureau stations, then the results will be very close to the station results. But in areas where the Bureau stations are far apart, like in the top end, for example, then the differences can be quite significant. So for example, if you look at the data for Darwin, the differences there are really quite pronounced, and that's because there are so few stations up in that part of the world. So that's the first thing. The second thing to think about is that if you're planning to compare the results from this tool with the results that you can get from the Bureau's Climate Data Online website, something to keep in mind is that they present results for the number of days greater than or equal to the threshold of interest. We don't do that. We only do the number of days greater than the threshold. So that's another source of difference between those two data sets. And the other thing to remember, if you go to the Bureau's Climate Data Online website to do a comparison of the results between here and there, pay particular attention to the baseline. When you first load up a data set on the Bureau's website, it will be using all of the available data. What we do here, of course, is we use the 1981 to 2010 30-year time period. So for most of the data sets on Climate Data Online, you can select that particular 30-year block, and then you're comparing like with like. Something else that happens when you use a model to infill between stations, particularly when those stations are spread out, is that you tend to smooth out the extreme events. So if you've got a really high rainfall event at one location, and then you've got to infill till you get to the next location, just by virtue of that infilling process, you're going to smooth out some of those most extreme events. So it's worth remembering that these results that we present here will be quite conservative. It would be possible to get a more or a less conservative set of results, but it would be very complicated and require dynamical downscaling. So it's a bit of a trade-off. And the other thing, as I mentioned, is the gaps, particularly with, well, only with rainfall. If I go back to the 99.9th percentile rainfall results. Now, I hope it's obvious that those blobs in the middle are not real. It's just an artifact of the AWAP dataset because it's just too great a distance between the stations in these regions. There are no data in these sections, or the data are pretty meaningless. So just keep that in mind. and you'll be fine. I think that's about it. Yep, I think I've covered everything I wanted to cover. So I hope that's clear as it can be. And I encourage you to go and have a bit of a play. And if you would like to provide us with some feedback, we'd love to hear it. We can, you know, by virtue of the NESP, we can continue to update and maintain the website. So it's going to be much more helpful if we hear from you to let us know what you think, rather than us just trying to come up with all the solutions. All right, I'll switch back to Sonia.
Great, thanks, John. We do have some questions coming in, and I would encourage anyone who's got a question to write it in the chat box at the side of the Zoom box now, so I can read them out to John. So I might start from the first question that came in from David Caroli, who asked, John, the approach used for future projections of threshold exceedance assumes no change in daily variability. Is that an important limitation?
Yeah, it is, and thanks, David. I should have added that to the list of caveats. It is actually on the in the limitations section that I showed you earlier underneath the tool. It does talk about this. It does assume that there's no change in the variability, and also, which can be quite significant, this method doesn't allow you to capture if weather systems are likely to move more slowly, for example. You may have seen in the media recently talk about climate change making weather systems hang around for longer, and this can impact obviously heat waves, but also flood events if a system is just moving much more slowly, and particularly if you combine that with the ability of the atmosphere to hold more rain and hold more water, and dump it in more extreme events, then it's sort of a double whammy effect. And yeah, that's an absolute limitation of this approach. There is quite a bit of work being done all around the world and in Australia, attempting to get a better understanding of how these extremes will change by using dynamical modelling approaches at high resolution. And the CRC for climate extremes is working on precisely that, and we do some work in that space as well. But yeah, that's a really good point, David. Thanks.
Okay, the next question comes from Paul B, who asks, are uncertainties within a model shown anywhere? You can get a sort of uncertainty between models, but how about within each model?
Okay, so if I understand your question correctly, Paul, the uncertainties within a model can come from a whole range of different, well, from 3 main sources, but fundamentally, I think perhaps what you're alluding to is the global, well, any model is constrained by the size of the grid box that it works with in calculating what's going to be going on in the atmosphere or the ocean. And the larger the grid box, the more climate features will have to be estimated rather than calculated dynamically in a process called parameterization. So a global climate model like, well, so the average grid box of a global climate model from the latest data set is about 180 kilometers, give or take. And you know, it's not hard to think of a weather feature that would be smaller than that. You know, just small scuds of rain that can come across, obviously form and go about their business at a smaller scale than that. So the global climate models have to estimate that in some way. So that's a limitation, but we assess the limitations of each model through an evaluation process. And if I can just switch back to the website for a second. Take you to the publications library. If you haven't already seen this, I would encourage you to have a look at the technical report. Chapter 5 of the technical report is about evaluation of the global climate models. And this was done using 9 different metrics, which looked at the sort of more routine things like, you know, how well the model projects temperature and how well it models rainfall, but also things like how well it simulates the climate drivers that are influential in Australia, particularly ENSO, southern annular mode, the monsoon, those things. And so for a model to get a high score, it had to do well on all of those 9 metrics. And conversely, if it didn't do well on 3 or more of those metrics, we flagged that model as a model to be wary of. Now, if you're using all of the model results combined together in what we call an ensemble, then that's okay. You can include those models. We determined that there were no models in the 40 model data set that should be excluded completely. So we left them all in there, but we've flagged that in certain regions and for certain parameters, you should be cautious. But if you're combining all the results, like I said, into an ensemble, then you can leave them all in. But for something like this thresholds tool, where we are looking at the results from individual models, we want to make sure that the model is as good as possible. So what we've done, as I alluded to briefly earlier, is in the selection of those 8 models, we avoided any of the global climate models that didn't perform in that top sort of section of the rankings, if you like. So these are all highly ranked models in terms of their ability to simulate the past climate accurately, as good as they can be anyway. So that's how we've handled that sort of intra-model uncertainty. There's not really any way around intra-model uncertainty, that it will always exist, and it doesn't matter whether you're using global climate models or regional climate models or even statistical climate models. The clue is in the name. They're a model. They're about allowing us to do experiments to explore what the future might be like, but they're not predictive tools. They give us a range of plausible future climates to inform our planning. So I hope that answers your question, Paul.
John,
if not, drop us an email and I can fill you in a bit more or point you to somebody who knows more about it than me.
So I've got a few follow-up comments on that question, John. So Paul says, I was thinking of a figure, say 10 days plus minus 0.5 days, for example. Does that?
No, sorry. So someone, I just noticed someone, David suggested that perhaps you're talking about differences between different runs of the same model. So, yeah, and internal variability. Yeah, so if we run the same model multiple times, we'll get different results. And so for the work that we did, climate change in Australia, we just, well, we included every run for some things, but for work like this, we just set a rule that we would use the first run available from each model. Otherwise, it just becomes overwhelming. And by looking at then the span in the results from all of the models, we're confident that that sort of within model range is actually encompassed by the full range from all the models anyway. So then when you're pulling out a single model like we're doing in the thresholds tool, you're just pulling out examples of particular parts of the range of projected change. If we're using this sort of information for impact assessments, then we encourage people to use a clustering approach to identify which parts of the projection range are most meaningful to your impact assessment and the decisions that have to be made. And we have an approach called the Climate Futures Framework that is designed to do just that. And that gets around the problems associated with using an individual model, because it allows you to identify which models are representative of the important parts of the projection space for your particular impact assessment. Hopefully that's...
Yep. All right, we might move on to a different question. So we have one from Herwin, who asks, do all the other tools cover the 1981 to 2010 time period as well? Previously, it was the 1986 to 2005 time period.
I'm glad you asked that. So, the reason for using the 1981 to 2010 time period is because we wanted 30 years of observed data. One reason, one of several reasons for that, was because if we went with 1986 to 2005, a big chunk of that period was taken up by the millennium drought. And even though, you know, you can argue the whys and wherefores of whether or not there was a climate change signal in the millennium drought, nonetheless, it is fundamentally a natural variability phenomenon, and we didn't want our historic data set to be so strongly biased towards dry with such a large contribution from natural variability. So by expanding the time range out to 30 years instead of 20, it reduced the effect of the millennium drought on that historic data set. Why not just choose a different historic data set time period that didn't have the millennium drought in it, I hear you ask? We have to have the historic data aligned with the baseline period for the projected changes from the global climate models. And that time period is set for us by the international community. The IPCC determined that for the 5th assessment report, the reference historic time period would be 1986 to 2005. So that's the period from which we compute the changes in future in the global climate models. Because we're taking those change values from the global climate models and combining them with historic data, we need to make sure we're mixing apples with apples. So our historic data has to also come from that same time period. But because we wanted 30 years, we just expanded it 5 years on each end. So it's still centered on the same year, still centered on 1995, but it just runs for 5 years longer on each end in order to get around that millennium drought issue. It's confusing, and it's doubly so because the change signal that's applied to the 30-year data set is computed over a 20-year time period. So it does get confusing. It is explained in more detail on one of the web pages if you are interested. Sonia, do we have a way of contacting people, sending stuff out to people who are on the webinar? Can't hear you. Sorry.
Yes, we have a Hub website address where they can, anyone who's interested can ask questions. On the end of your slide pack, John, there's the info@nestclimate.com address, so people can send emails through there if they're interested in more information.
Cool. So if anybody, if people are interested, I can send some links to particular pages of the website, and you can have a bit of a read. Because I've just had a brain freeze. I can't find the web page at the moment.
All right, well, shall we move on to, we've got another couple of questions I'd like to squeeze in. So we've got a fantastic question here about, would you be comfortable with stakeholders using the mean value of the 8 models, mean value provided within the pop-up table, or would you still advocate using a best and worst case scenario?
Oh, okay. I would strongly advocate a best and worst case scenario if it's appropriate for the purpose. So if you're definitely if you're doing an impact assessment, then you should be, we would argue, using a best worst case kind of approach. But if you're communicating to you know, to the board of management, or to your local councillors, or to a community group or something like that, then there's no need necessarily to go into that level of detail. And so in those sorts of circumstances, then talking about the thresholds as a mean with a range would be perfectly appropriate. But I wouldn't just use the mean in isolation. We should always have the mean with the minimum and maximum, so that people can see always that there is a range in this. People have a tendency to want to latch onto a single number for these things anyway, which is just natural. So it's important that when there is a range, we make sure that it's explicit. Now, people may still zoom in on just the biggest value, or the smallest value, or the mean, but it should at least be there. It's really important that we don't obscure the fact that there is a range in these results, because, you know, after all, these are just model data. It's not the truth. It's our best attempt at getting to meaningful, plausible future information.
We have another question from Liz, who asks, "Hi John, can you give a few examples of innovative ways that people have or are using this tool?"
I know of some people in the agricultural space who are who've been using this sort of approach. In particular, in the dairy sector, they're very interested in those the daily minimum temperatures, which, you know, roughly equate to the overnight lows, the overnight temperatures. You know, on a sort of normal day where it gets cooler at night than it has been during the day. That's what they represent. Dairy cows cease producing milk if they have more than a certain number of days above a particular temperature overnight. And so, yeah, the dairy producers are very interested in those kinds of metrics. They're the only ones I can think of off the top of my head. We've presented them and talked about them a lot in the context of human health as well. And some of this has been in the media as well, you know, in the last 6 months or so. And some of that media attention has highlighted the fact that our projected threshold, in particular in terms of maximum temperature, are really quite conservative, and that in places the actual number of days a year has already exceeded what our projections say for 2030. Got to be careful with that, though, that you're not confusing, or that you're not getting taking too much notice of what is natural variability, because remember, these results are the 30-year average result, so there's going to be variation around that. So that's not unexpected.
Well, we've got one last question I think we can just squeeze in. Comes from David. So he says, "Have you compared your results using the new threshold tool with the major cities' thresholds using the older method, for example, the capital cities?"
Yes, but not with this version of the tool, but the underlying data are the same. It won't have changed. There are differences because they used multi-model ensemble changes, whereas we're using individual models, so there's a different approach. And I think from memory, and apologies if I've got this wrong, but it's in the technical report, but I think from memory, they were using station data, or possibly another product called Acorn Sat, which is a temperature data set that the Bureau has, high quality temperature data. And yes, there are differences, but I don't know off the top of my head whether there's any consistent pattern or whether they're just sort of random.
All right, well, we might wrap up there then. Thanks everyone for your great questions, and thank you, John, for a fantastic demonstration of a really great tool. Just a little plug for the Hub's next webinar, which will be held on the Wednesday, the 20th of March, and that'll be provided by Dr. Julian O'Grady from the CSIRO on the topic of understanding future extreme sea levels, tools, information and support, and information to support coastal management. So more of a coasts look next week, but again, still some tools as well. So I've just noticed that we've had a little comment come in from Tim Irwin to say that in terms of how stakeholders have used the threshold tool, that the tool's been used to look at impact on apple crops. So that's a, and he's added a link there for those who can see the pop-out box. So that's an interesting example of how stakeholders use the tool as well. So, so thank you once again. Please tune in for next month's webinar. As usual, there'll be an email invitation to register that'll come around. And thanks again, John.
My pleasure.
Okay. Thank you, everyone.
Cheers.